Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI-generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In the previous videos 43 and 44, we explored matrix multiplication using the MKL routine with OpenMP for parallel computing, applying the Cray Fortran compiler loaded through the Cray module system. In video 42, we performed matrix multiplication using a triple nested loop with OpenMP for parallel computing, utilizing the Cray Fortran compiler loaded through the Cray module system. In this video, we will once again use a triple nested loop with OpenMP for parallel computing, but this time utilizing the Intel Fortran compiler loaded through the NRIS module system. One reason for using the NRIS module system is that it currently offers a wider range of available software compared to the Cray module system. We will also do a scaling analysis. This analysis involves measuring computation times while varying the number of threads, starting with a single thread and scaling up to 256 threads. Scaling analysis is a technique in parallel computing used to assess how effectively a system performs as more processing units are added. It helps identify whether increasing computational resources leads to performance improvements and to what extent. This process is vital for optimizing parallel systems and ensuring resources are utilized efficiently. In video 41, I reviewed information about the new Olivia Linux cluster available on the Sigma 2 documentation pages. In this video, I will focus instead on the NRIS module system on Olivia. The HPE Cray system includes its own module system, and we applied this system in videos 41, 42, 43, and 44. Additionally, the NRIS module system will be provided, similar to the one used on Betsy, Saga, and Fram. There are three separate module systems, one for GPU nodes, one for CPU nodes, and one for login nodes. In this video, I will be using the CPU module system. I am already logged in to Olivia and currently inside the MXM OpenMP folder. I will begin by listing the contents of my folder. I have created a folder named NRIS Intel. Let me navigate to this folder using the cd command. Before looking at the Fortran program using the triple nested loop and the script for executing this program, I will clear the terminal. I will first list the contents of my folder. Let's start by examining the Fortran program that performs matrix multiplication using the triple nested loop. I will begin by testing the program with a matrix dimension of 32, 7, 68. Otherwise, the program remains as described in videos 41 and 42. I am using allocatable matrices in this program as explained in video 42. After reviewing the code, we exit the Emacs editor and return to the terminal. We will now examine the job script used to execute the Fortran program. The job script is largely the same as shown in video 41, but this time I will use the NRIS module system instead of the CRE module system. The module restore system command ensures that modules from the home environment are not passed to the job. Currently, my home environment uses modules from the CRE module system. By using module restore system, we ensure that these modules are not applied to the job. Instead, the job script explicitly loads the NRIS CPU module system. I will load the Intel module from the NRIS module system since we will explore matrix multiplication with the Intel Fortran compiler. The script compiles the Fortran program using the Intel Fortran compiler with the same options applied on Betsy. I am now using both Xhost and IPO, along with the notable qopt-mat-mul option, which replaces the triple nested loop with a highly optimized routine. With the NRIS module system, I do not have access to the CRE module system. Therefore, I must use the Xhost option, as I cannot utilize the CRE AMD Turin module provided by the CRE module system. After exiting the job script and returning to the terminal, I can clear the terminal. I can execute the Fortran program by submitting the job script to the Slurm queue system. We can see that the job is assigned the number 3999. When I check the Slurm queue using the sq command, we can see that the job has been computing for 20 seconds on the C199 node. Using the more command, I will open the Slurm job output file. The job output file first lists the NRIS modules that are used, and the list was generated by the module list command in the job script. The matrix multiplication using the Intel Fortran compiler was completed in about 30 seconds using 256 cores. On FRAM, the same matrix multiplication was completed in about 67 seconds on 32 cores. On Betsy, it took about 40 seconds, and only 32 seconds when using the math kernel library, MKL, on 128 cores. The job output file shows that the job had an CPU efficiency of about 81% and used about 26.8 gigabytes of memory. I will now perform a scaling analysis using the triple nested loop with the Intel Fortran compiler loaded through the NRIS module system. But first, let me clear the terminal. I will first list the contents of the folder in the terminal. The scaling analysis will measure computation times with different thread counts, starting from a single thread and scaling up to 256 threads. Rather than using the approach from videos 12 through 16, I will follow the method from video 44. This approach involves using a Python script named setup testing OpenMP for the scaling analysis, so let's take a look at it. The script uses the OS module to execute Linux commands and was previously reviewed in video 44. Let's exit the Emacs editor and return to the terminal to review another file used in the scaling analysis. This file is the job script named testing OpenMP. Let's take a closer look at it. The script is very similar to the job script I have used in this video. The first difference is that it requests one node, but the number of tasks and CPUs per task, or threads, is specified differently and not directly in the script. The second difference is that the job requests 753 gigabytes of memory. The reason for this is explained in video 44, and this ensures that each scaling test job is executed exclusively on a single compute node. The third difference is that the script does not compile the Fortran program, but instead uses the compiled executable I have produced in this video. The program is executed 3 times, and the resulting wall times can be used to calculate an average for matrix multiplication using the triple-nested loop with OpenMP. After reviewing the testing OpenMP script, we exit the Emacs editor and clear the terminal. I have the Python module in my home environment as explained in video 44, and will begin the scaling analysis by executing the Python script. The terminal displays the sbatch commands executed by the script. We can see that the number of tasks and CPUs per task is now specified on the command line when submitting the testing script. Applying the slurm-q command, I can confirm that all my jobs have started. Before checking the results, I will clear the terminal. I use the ls command to list the folder contents. Let's examine the last job output file using the more command. From this file, we see that using 256 threads result in a wall time of approximately 35 seconds. We observe that the memory usage is about 27 gigabytes. The data from these scaling tests can be used to create figures showing the wall time and CPU time, similar to the approach used in videos 12 through 16. The first figure displays the wall time and CPU time using a logarithmic scale on the time axis. The second figure presents the same data but uses a logarithmic scale on both axes. Let me first enter the number of threads or cores used in the scaling analysis. I can add the mean wall times to the figure. I will also enter the CPU times, calculated by multiplying the wall times by the number of cores used. Finally, I include the speedup factors between tests. The CPU time was plotted to show that, in an ideal scenario with perfect scaling, the curve would form a straight line, reflecting a consistent speedup factor of 2 across all tests. We observe a near-perfect speedup up to 16 cores. The scaling analysis shows that a computation taking about 1,202 seconds on a single core is reduced to approximately 84.8 seconds on 16 cores, achieving a speedup of around 14.2. In an ideal scenario with perfect speedup, this would have been 16. The speedup decreases when scaling from 16 to 64 cores. The scaling analysis indicates that a computation taking approximately 84.8 seconds on 16 cores is reduced to about 35.2 seconds on 64 cores, achieving a speedup of roughly 2.4. In an ideal case with perfect speedup, this would have been 4. The speedup diminishes further when scaling to 128 cores, eventually resulting in a slowdown. The scaling analysis shows that a computation taking 35.2 seconds on 64 cores increases to approximately 36.1 seconds on 128 cores, resulting in a slowdown factor of about 0.98 instead of the ideal speedup of 2. The speedup improves slightly when scaling to 256 cores. The scaling analysis indicates that a computation taking 36.1 seconds on 128 cores decreases to approximately 34.8 seconds on 256 cores, achieving a speedup factor of about 1.04 instead of the ideal speedup of 2. The scaling analysis shows that a computation requiring 1202 seconds on a single core is reduced to 34.8 seconds on 256 cores, achieving a speedup of approximately 34.5, which falls significantly short of the perfect speedup of 256. A perfect speedup is unattainable because, as explained in video 11, there will always be sections of a program that cannot execute in parallel. These sequential sections increasingly limit the speedup factor as the number of cores used for parallel computing grows. As observed in these scaling analyses, there is near-perfect speedup up to 16 cores, but this diminishes when scaling to 32 and 64 cores. The speedup factor declines even further when using 128 and 256 cores, with a slowdown occurring at 128 cores. The observation that scaling analysis can reveal a slowdown may be surprising, but it highlights the importance of such analyses in avoiding incorrect assumptions that adding more cores always improves performance. In the next video, we will explore the performance of the NRIS Intel compiler when using the MKL routine for matrix multiplication. I am looking forward to the next video. Wishing you all happy computing in the meantime.